Okay, so in this lecture, I want to say some very basic stuff about calculating probabilities. We might or might not get to the second part of Weisberg's book where he talks about more advanced stuff with calculating probabilities, but I just want to say something about very basic calculations with probabilities and inductive logic. As you guys might have guessed, since I'm using the word calculating, we are going to be talking about some math. You should neither get excited nor scared with this. If you really love math, you shouldn't get excited because it's not going to be terribly complex or interesting math. If you really hate math, well, you shouldn't get scared because it's not going to be complex. Adding and multiplying fractions, pretty easy stuff. All right, so I'm not going to spend a lot of time on this because I think Weisberg does a pretty good job with it. I'm just going to go through it again, to reinforce some concepts. So it's really important when we talk about calculating probabilities that we know what we mean by mutually exclusive and independent. We already talked about independent. Mutually exclusive isn't a hard concept either. Independence, remember, just means that A being true doesn't affect the probability that B will be true, right? If I flip a coin and get heads on the first flip, well, the second flip is independent of that because the first flip really does nothing to affect the probability of the second, right? Mutually exclusive just means that both things can't happen, right? If I flip a coin, heads and tails are mutually exclusive, right? It cannot come up both heads and tails. So mutually exclusive means they can't both be true. Independent means that the one does not affect the probability of the other. Now, the book, when explaining this, actually refers to Venn diagrams. And I realize we actually haven't talked about these yet, which is kind of an oversight on my part, honestly, because they're actually pretty interesting. And when you get to logic and some of the stuff in math that touches on logic, like set theory, Venn diagrams are actually really good at explaining the concepts, making things clear. They're also good with just logic and probability for this stuff. And so Venn diagrams are when you take circles. I'm going to use 2 circles because they're simpler. You can use up to 3, and you use those circles to illustrate how 2 propositions or claims or even mathematical formulas sometimes relate to each other, right? So, in this one, we could treat our sort of salmon-colored circle and our gray circle as A and B, right? In this one, A and B overlap. We can use these Venn diagrams to illustrate some more interesting relationships between propositions, right? So in this one, let's say that our salmon-colored one is A and our gray-colored one is B. Well, mutually exclusive ones, there's no overlap, right? The salmon one here, all the cases of A, gray, all the cases that B. Well, in any case where you have A, you're not going to have B, right? This illustrates the 2 are mutually exclusive. There is no overlap whatsoever between cases of A and cases of B, right? That's what we mean by mutually exclusive. The Venn diagram, these are kind of important in their own right. I hope also they serve to make this idea a little clearer. Independent propositions, on the other hand, overlap, right? There are cases where one is true and the other one turns out to be true as well, right? I'll give you guys an example, right? If you flip a coin once, well, there's no way that it can be both heads and tails, right? Case where it's heads, case where it's tails on the one flip, completely separate. There's no overlap, right? But imagine you flip a coin twice. Well, how the two coin flips come out are independent of each other, but there are going to be some cases where you get heads on the first one and tails on the second one, right? The one doesn't affect the other, but there are cases where one is true and the other is true as well, right? Independent propositions, the Venn diagrams will overlap. There are cases where you get heads on the first flip and tails on the second, right? Hopefully that's clear to you guys. Hopefully that, illustrates the difference. You know, it is very important to keep independence and mutual exclusivity separate from each other. They're not the same thing. They're importantly different. All right, so why do we need to know these rules? Well, some basic concepts and how to figure probabilities depend on it. When A and B are mutually exclusive, then the probability of A and B equals the probability of A times the probability of B. An example with flipping coins, H1 probability that heads on the first flip, H2 probability that heads on the second flip. What are the probabilities that you get two heads in a row, right? Well, these are independent, so you can multiply them. 1/2 times 1/2, 1/4, right? Pretty easy, not difficult math, hopefully. Now, one thing to keep in mind is that the multiplication rule does not work with dependent events. If A affects the probability that B, then you can't multiply them. Or you have to do something much more complicated, right? You can't just multiply them in the way the multiplication rule says to do. I'll give you guys an example, right? What is the probability that you get both heads and tails on the first coin flip, right? Well, of course, it's absolutely 0 because you can't have heads and tails, right, on one coin flip. If you tried to multiply those two, though, you would get this bizarre result that says, well, 1/2 times 1/2 equals 1/4. That's just crazy. It's not even possible, right? Or I'll give you guys another example, right? Let's take one with the election, right? Let's just say that, Trump and Biden both have a 50-50 shot, right? So if I say, well, what's the odds that Joe Biden will be president and the next president will be a Democrat? Well, I say, well, 50% chance it'll be Biden, 50% it's a Democrat. So multiply those two. What are the odds that it's Biden and a Democrat? 25%, right? That's just bizarre, right? Same if you took Trump and a Republican, 50-50, 25% it'll be both Trump and a Republican. It's just crazy, right? Obviously, whether it's a Democrat relates to whether Biden gets elected, whether it's a Republican relates to whether Trump gets elected. So you can't just multiply the propositions or you get these crazy results, right? So when events are dependent, multiplication rule doesn't work. Even next lecture, there's a lot going on here. We won't get to all of it, but even next lecture, we'll say a little bit about, how we figure out the odds of dependent events. When we start talking about conditional probability, that'll help us to see a bit more here. All right. But for now, let's just talk about the addition rule. And the addition rule says that when A and B are mutually exclusive, then, this disjunction probability of A or B equals the probability of A plus the probability that B. Really simplest possible example. What are the odds that you get heads or tails on the first flip of a coin? Well, 1/2 that you get heads, 1/2 that you get tails. Odds are 1 or 100%, right? 2/2, 100%. The book's example, a little more complicated. What are the odds that you get one heads, one tails on two flips of a coin. Um, this one's actually a little more complicated, right? So, you have these two independent events, H1, H and tails 2, T1 and H2, right? Multiply them, then you multiply them, you get 1/4, then add them, you get 1/2 or 50%, right? Now the book's example can be a little confusing, but I actually think it's really important because you have to be really careful how you symbolize or describe events, or you're going to get crazy, stupid results, right? If I just tried to set this up, well, what's the probability of heads or tails, or sorry, one heads, one tails, and two flips? If I said, well, heads or tails, 1/2 plus 1/2, then you get this crazy result that it's a sure thing when it's not, right? Heads on the first flip is a different thing from heads or tails on the second flip, so you have to be really careful how you describe or specify events. You can't just say heads or tails when you have multiple flips. You have to specify heads 1, tails 1, for the first flip, tails 2, heads 2 for the second flip, right? But the book's example, you have, if you have two flips, 4 different possible outcomes. 2 of those outcomes have one heads and one tails, right? So hopefully this makes sense, how the addition rule is supposed to work for these fairly simple cases. Now, one thing to keep in mind is that the addition rule does not work when events are not mutually exclusive. Your book has a really memorable example. Say we hear it's a 90% chance of rain this morning, 90% chance of, rain in the afternoon. What's the chance that it rains in the morning or afternoon? Well, obviously it can't be 180%, right? Outside of stupid TV ads, the probability of something happening can't be 180%. It just doesn't make any sense, right? Or, take another one. If I say, well, what's the probability that Biden is elected or a Democrat is elected? Well, 50-50 for each of those, maybe. And I say, well, so there's a 100% chance Biden is elected, right? Same argument would get you a 100% chance Trump is elected. It's a chance of a Republican or Trump, 50-50. Not only is it fishy that you can do that and go from 50-50 to 100%, the argument obviously is crazy because it can't be true that both there's a 100% chance Trump's elected and a 100% chance Biden's elected, right? So if you try to run the addition rule on events that aren't mutually exclusive, like rain in the morning and rain in the afternoon, or Trump getting elected and a Republican getting elected, or Biden getting elected and a Democrat getting elected, then you're going to get really stupid results, right? So only use the addition rule for disjunctions with events that are mutually exclusive. Otherwise, dumb stuff happens. Some more stuff on calculating probabilities. The probability, think about deductive logic. We think about tautologies. Tautologies are statements that are true by definition. In inductive logic, the probability of a tautology is always 100%. Probability of A or not A equals 100%. Now you guys might be thinking, okay, why in the world does he bring that up? How in the world could that possibly be useful? That's just dumb. Well, actually, this probability of A or not A equaling 100% will actually be useful in some cases, and we'll talk in next lecture, or maybe actually the lecture after, how that might be. Probability of a contradiction is always 0. So probability of A and not A, always 0. A and not A, remember, is a contradiction. That can't possibly be true. Final thing, probability of logically equivalent propositions is the same. Your book uses an example of this. If A and B are logically equivalent, then A and B have the same probability. That doesn't work the other way, by the way. Just because two things have the same probability doesn't mean they're logically equivalent. But if they are logically equivalent, then they do have the same probability, right? But if you think back to the rules we've learned about, what works in propositional logic, you can think of some more interesting stuff, right? So the same sort of De Morgan's rules and distribution and things like that. Actually, I don't think we've talked about distribution, but the stuff about being able to rearrange in conjunctions and disjunctions, all of that works for inductive logic too, right? So probability not A or B, you could use De Morgan's rules on that, and probability, A, not A or B is the same as not A and not B. So the probability of not A or B would be exactly the same as the probability of not A and not B, right? In deductive logic, the truth values of logically equivalent propositions are always going to be the same, always going to have the same truth value on the truth table. In inductive logic, the probabilities are going to be the same. All right. Hopefully that all makes sense to you guys. Most of this is just going back through kind of quickly what Weisberg does, just giving it another run. So hopefully none of that is really, mystifying.